Welcome to the lesson 21 of industrial instrumentation. In this particular lesson, we will do some exercises. That means, I will give you some problems and also will provide the solutions. The best way to solve the problem, you first do not look at the solution, first try to solve the problem and then see whether whatever the answer you got it, then that is getting tallied with the results which we have given, right. So, we will particularly solve in this lesson the problems on the LVDT and then pH probe and McLeod gauge. As you know, the McLeod gauge is used for the low pressure measurements, pH is used for the pH probe is used for the pH measurements, and so LVDT already we have covered. So, we will sort different types of problems of LVDT, right. So, let us look at the contents of this lesson. So, these are problems and solutions on industrial instrumentation. The contents are the problems and solutions, LVDT, linear variable differential transformer, pH meter as well as McLeod gauge, right. So, let us look at the problem. The problem 21.1, you see it is telling in the figure shown below, which will become in the slide 4. Let xi be a periodic motion with significant frequency, that you can see, that is no problem. You can see here this is our LVDT, right, with the phase sensitive demodulations. You see there we have used here 4 diodes here, and we have discussed this in details, right. So, we make the algebraic summation of the two voltage to get the voltage output, and this is a input to the systems, and this is excitation. Ex is the excitations of our LVDT, and xi is the input motions or the input of the system, and UO is the output of the system of the LVDT, right. Let us go back. In the figure shown below, let xi be periodic motion. So, this time we are measuring the periodic voltage periodic signals, right. So, in the figure shown below, let xi be a periodic motion with a significant frequency content up to 500 hertz, and the excitation frequency is 5000 hertz. The output signal obtained is then passed through a low pass filter and then to an oscilloscope with an input impedance of 10 to the power 6 ohm. So, just you can see, just for the sake of problem solving, so you have taken usually the input impedance are slightly more or even 10 mega ohm or more. So, it is in this case we have taken 1 mega ohm. We desire the ripple due to higher frequencies to be no more than 5% of the unfiltered value, right. Find number A, find the frequency range after the modulation process. Excuse me. Design a low pass filter for the above application. Also calculate the value of R in the figure. Okay. The resistance values which we have shown in the diagram, that resistance you have to calculate, and C, calculate the time lag introduced due to the low pass filter, right. Okay. This is our all the problems. So, this we will solve one by one, right. So, let us see, let us look at how we can solve this problem, right. Now, take me a blank page. Right. The diode bridge shown in the figure, as you know, act as a phase sensitive demodulator. Now, frequency of the motion is 500 hertz, right. The frequency of motion is 500 hertz. This is actually is FM, right. The carrier frequency FC is 5000 hertz, right. And after the modulation process, other than the motion frequency, we will have frequencies, two frequencies we will get. The two frequencies are 2fc plus m plus fm equal to, this will become 10,500 hertz, and 2fc minus fm, this is 9,500 hertz, right. Excuse me. Thus, we can say that the frequency range will lie within these particular signals which we have given. Now, this is the problem, I mean A we have solved. Now, let us look at the part B. In part B, we are telling that the design a low pass filter for the above application, also calculate the value of the resistance R of the phase sensitive demodulator circuits as shown in the figure, right. You see, let us go to figure, so it will be more clear. So, let us take a new, first to go back, right. So, you can see here. So, this is our figure. So, these R we have to calculate, and the low pass filter, because we need a low pass filter to get the actual signals, that is the movement of this one, okay. Corresponding to that, what is the voltage output that we will get. So, we will find that thing. So, let us take a blank page again, right. Now, in order to design the low pass filter, we first need to choose excuse me, we first need to choose the order of the filter that will give us our desired result. Now, let us first consider a first order filter, right. The first order filter will look like okay. This input is coming from the phase sensitive demodulator output. These outputs we are designated as E1, and this resistance is RF, and this resistance is CF, right. Let us choose that. Now, as you know, we will have E1 by EO j omega will be given by 1 upon j omega RF CF plus 1. Now, it is given in the problem that the ripples due to higher frequencies to be less than 5% of the unfiltered value. So, for higher frequencies we consider the 9,500 hertz and above. Okay. So, if it is 9,500 hertz, then obviously I can write the equation which looks like this, that 0.05 equal to 1 upon root over omega square tau f square plus 1, where tau f equal to RF into CF, that is the time constant of the filter circuits just we have drawn, and omega obviously is equal to 2 pi into 500, right. Sorry, this is, if I take so omega is equal to 2 pi into 9,500. So, or tau f, the time constant of the circuit, will be given by 0.0003348 second, right. For this TF we have the amplitude ratio, you know. So, for this TF the amplitude ratio will get, that means E1 by EO, you take mod of that, it will become 1 upon root over 2 pi Fm tau f whole square plus 1. So, this will give you 0.69. Thus, we see that the high frequency portions of the Xi will be distorted considerably, right. So, high frequency component of this xi, that means the movement, xi is the movement to the our LVDT code, okay. So, that will be distorted considerably. So, this inference is that this type of first order section will not be suitable for this type of application. So, let us take a second order section, right. So, if you take a second order section, it will be like this. The filter will look like, these are all passive filters. So, most of the cases it will suffice, because if you use the active filter, there are some advantages, but there as well there are disadvantages also. This is E2, right. This is RF as before, this is EO, this is CF. So, this is 10 RF we have taken, and this is we have taken 0.0 CF, right. So, E2 by, I can write E2 by EO j omega is equal to 1 upon j omega RF CF plus 1 whole square, right. Now, again let us check whether this is good for my work. So, 0.05 that we have done before also for single order filter, omega tau f square plus 1, right. So, tau f will come up as 0.00731 second, right. So, tau f will come up as, so I can write like here. So, the tau f will come up as 0.0000731 second. So, if I look at the amplitude ratio for the second order case, so the amplitude ratio for the second order case will be amplitude ratio for the second order case is given by E2 by E0 equal to 1 by 2 pi Fm into tau f square plus 1. So, this will give you 0.95, right, clear. So, this will give you this value. I think there will be one square root here, is not it. So, this will give you the, thus we see that the amplitude ratio from omega naught will be, so the amplitude ratio from the omega naught, I am sorry. So, actually this will be, let me write down again. So, the amplitude ratios will be E2 by E0, E2 by E0 equal to 1 upon 2 pi Fm tau f square plus 1, which will give you 0.95, right, clear. So, if this is the case, so I can say that the amplitude ratio from omega 0 to is nearly flat. That means the amplitude ratio from omega equal to 0 to omega equal to 3146 radians per second is nearly flat. That is from 1 it will be 1 and it will fall to 0.95, right. So, it is reasonably good. Now, in order to determine the values of RF and CF, we use the fact that each stage in the process must have an impedance 10 times more than that of the previous stage. Now, you see the oscilloscope has an input impedance of 1 megohm, is not it. if the oscilloscope has an input impedance of 1 megohm, I can write 10 RF equal to 10 to the power 5 ohm. So, RF we can take equal to 10 to the power 4 ohm, right. And now CF into RF equal to 0.0000731. So, CF will be equal to 73 into 10 to the power minus 6 by 10 to the power 4. So, it is coming up as 0.0073 microfarad, right. So, ultimately we will get the circuit which will look like the filter circuit. Let me take a new page. Sorry, this will be again, right. So, let us go to pin. So, this will be again resistance. Okay. So, let me take the eraser again. So, this is gun. So, taking pin. So, this will be a capacitor, right. So, between this we will take the output, right. Here I will get the input, or I can say that between this and this the output from the phase sensitive demodulator will come, and here the output from the output which will go to the oscilloscope, right. The values are 10 kilo ohm, 100 kilo ohm, then 0.0073 microfarad, 0.00073 microfarad, right. Now, the third part, the part C, we have to find the phase angle. So, let us do that problem. Let me take a new page. So, the problem solution to the part C of the problem, problem 21.1. To determine the phase angle, a phase angle E2 by E naught j omega minus of tan inverse 2 omega tau f upon 1 minus omega square by tau f square. So, this will give you minus 25.8 degree, right. So, the phase angle will introduce a delay which can be computed as, so the delay it will produce will be given by 25.8 upon 57.3 into 3140, which is equal to 144 microsecond. Okay. These are all the solution to the problem number 21.1. So, now we will go to the problem 21.2, that is also an LVDT. So, let us look at that, right. Problem 21.2. In the following figure, a voltmeter with a finite input impedance Rm is connected. Find the expression for the frequency at which the phase shift will be 0. In many situations, this is very good problem is to know. They say the manufacturers also will give you some frequency, the manufacturer of LVDT will give you the frequency where the phase shift will be 0, right. So, it will be utilized, that frequency can be utilized to make the input output phase shift 0, because you see that we have seen when we discuss ABDT, to kill this phase shift we have to use lead lag network. In the case of leading phase angle we have to use a lag network, in the case of a lagging phase angle we need a lead network. So, that type of additional circuitry we can dispense of if I use a particular frequency of signal when there is no input output phase shift, right. So, it is important in that case. So, how will I know? How will I know what is the frequency where the phase shift will be, input output phase shift will be 0? Okay, once you solve this particular problem 21.2, so we will find that we can find the frequency where the phase shift is 0. Typically, the manufacturers also supply this particular frequency, right. Let us go. Now, this is our circuits. So, let us go back. You see, this is our, in the following figure, a voltmeter with a finite input impedance Rm is connected. Find the expression for the frequency at which the phase shift will be 0. Okay, this is our circuit. Okay, you can see here. So, we have connected a voltmeter here at least. See, we have connected a voltmeter here. Okay. We have connected a voltmeter here, right, to get a phase shift, to measure this voltage, right. So, let us first compute, right. All the values are given. LP is the inductance of the primary side, in the resistance of the primary side. Ls is the inductance of the one secondary. Lx is the inductance of the another secondary. Okay. So, we should have one core here which we have not shown, right, which has a movement xi, right. So, this is our problem. So, let us solve the frequency, let us find the frequency when the phase shift will be 0, right. Let us take a blank page, right. You see what will happen here. Anyway, let us first go back to the let us take a blank page. So, this is the problem number solution to the solution to the problem 21.2, right. Now, analyzing the above circuit, we have seen that we can write the circuit equations like this: IP Rp plus LP DIP. D is the delta operator, we have seen that thing many times before. M1 minus M2 D, that means D means, as we know, d by dt, right. So, in this case you see what is that, you see here, this is d means d by dt, right. So, it will be, in this case it will be dis by dt, in this case it will be dip by dt, right. Right. Just take the pen again. Fine. dis minus excitation voltage equal to 0, right, and M1 minus M2, okay, in the secondary side also we can write into dip, the color of the pen changed, it does not matter, Rs plus Rm into Is plus 2 Ls dis is equal to 0. So, this will give you the output which will look like, let us take this pen, E naught by excitations D equal to Rm meter impedance M2 minus M1 D upon M1 minus M2 whole square plus 2 LP LS d square plus LP 2 RS plus RM plus 2 LS RP D plus 2 RS plus RM RP, right. Let us take new page. So, the E naught by E x I can write in S domain equal to R m M2 minus M1 S upon M1 minus M2 whole square plus 2 LP LS multiplied by S square second order system plus LP into 2 RS plus RM plus 2 LS into RP S plus 2 RS plus RM into RP, right. These equations if I write in the j omega domain, so it will look like E x equal to j omega R m M2 minus M1 upon j omega LP 2 RS plus RM plus 2 LS RP plus 2 RS RM LPLS like this one. See, now if I want to make the phase shift input output phase shift 0, then you see that this term, that means if I take a different pen, this term, okay, this term and this term will be 0. Then j omega j will cancel out, so it will be only the no imaginary part. So, there is no phase shift between input and output, otherwise there will be phase shift, right. So, this entire term, that means 2 RS RM multiplied by RP minus omega square M1 minus M2 whole square plus 2 LPLS should be 0, right. So, that obviously then I can make that, I can say that to make the phase shift 0, okay, that to make the input output phase shift 0, so the last term of the denominator is to be 0. So, let us do that, take a new page, fine. So, that means to make phase shift 0, I will make take another new page. So, that to make phase shift 0, 2 RS plus RM RP minus omega square M1 minus M2 whole square plus 2 LP, let me take eraser, that means 2 LP LS will be equal to 0. Therefore, omega will be equal to root over 2 Rs plus Rm Rp by M1 minus M2 whole square plus 2 LP Ls, right. So, obviously, at that frequency when there is no phase shift between input output, our input output relations will be E naught by E x j omega will be equal to R m M2 minus M1 upon LP 2 Rs plus Rm plus 2 Ls Rp, right. So, this is our final expressions. Clear? Now, let us go to the problem number 20.3, right. Now, 21.3 I am sorry. Design a linear variable differential transformer LVDT based on the following details. What are the details? Let us look at. Supply frequency is 10 kilohertz, length of the core LA should be 20 centimeter, maximum distance of the core from null position, that means maximum movement of the core from the null position, okay, is 6 centimeter. Error introduced due to nonlinearity is 10%. Maximum EMF induced in the secondary coils E0, that is a 0.5 volt, I am sorry. Current in the primary for maximum EMF in the secondary is fixed also 20 milliampere. We assume that number of turns in the secondary to be which is Ns 4 times the number of turns in the primary. As you know, the number of turns in the secondary is always higher, right. So, you have to design this LVDT, right. So, let us proceed in this particular design. Let us take a blank page. Okay. So, the net induced EMF E j omega of the secondary coils is given by E j omega. So, this is a problem solution to problem 20.3, right. So, the net induced EMF, E j omega of the secondary coils is given by j omega I p 4 pi n p n s mu naught p x upon 3 s natural log r o by r I multiplied by 1 minus x square by 2 p square, right. Now, we have taken the standard notations for this, and we can write obviously that E naught, if I take the mod of this. So, this will be we have used all the standard notations. As you know that to solve this problem we must refer to the our lessons on the LVDT, right. So, because I do not like to repeat all these notations which I have used. So, if you once the person attended that particular lessons, he can also solve this problem. So, same notations we have used in solving the problem also, right. Now, E naught obviously I can write omega I p equal to 4 pi n p n s mu naught p x 3 s natural log r o by r I 1 minus x square by 2 p square, like this. We know from the text that the ratio r I by L A is about, right, is the ratio r I by L A, that means r I by L A typically is 0.05, right, both are in meters or in centimeter, then it is. Therefore, the inner radius of the LVDT assembly. So, the inner radius of LVDT assembly will be, that means Ri will be equal to 0.05 into 20, because 20 is the length already given, length of the, I think, primary, right, length of the primary is 20 centimeter. So, it is coming as 1 centimeter, right. The ratio RO by Ri varies between 2 to 8. So, let us take, that means ratio RO by Ri, it is also given, varies between 2 to 8. Let us take RO by Ri 4. Then the outer radius of the LVDT assembly is equal to 4 centimeter, right. Now, length of the primary winding. So, the outer radius, let me write RO. So, since this is 1 centimeter, so 4 into 1, so it is 4 centimeter, right. Now, length of the primary winding will be given by, take a new page, length of the primary winding, winding will be equal to P equal to x max upon 2 epsilon. So, this will come up as 6 upon 2 into 0.1, right, 2 into 0.1, where epsilon is the nonlinearity. So, which is, we are saying 10%, right, 10% nonlinearity. So, 0.1. So, it will give you the value of, and since it is 6 is the maximum displacement of your LVDT core. So, it is coming up as 13.4 centimeter. So, let us take it 14 centimeter, right, say, right. Now, length of the secondary windings will be, so the length of the secondary winding S will be equal to P plus x max is equal to 20 centimeter, right, 14 plus 6, it is 20 centimeter, right. Now, in equation 1, if I go back, the equation 1 means that the, which is the mod 1, right. So, if I go back, whether I can see, yes. So, this is the equation 1, right. So, the equation 1, let me take a new page. Now, from the equation 1, when E naught mod of E naught equal to 5 volt, IP equal to 20 milliampere, putting the values of P, S, RO by Ri and omega, that means putting the value of P, S, RO by Ri, omega in the equation 1, and noting that the maximum EMF is induced at the maximum distance from the null positions, we find that taking permeability of the free space as mu naught as 4 pi into 10 to the power minus 7 Henry per meter. So, we will get the value of, we can write down, that means if the left hand side E naught is 5 volt. So, 5 volt it will come up as 6 point, after plugging in all these value P, S, RO by Ri, omega in equation 1 and putting mu naught equal to 4 pi 10 to the power minus 7 Henry per meter, we will get on the left hand side, we will get 5 because E naught is 5 volt, that will be equal to 6.28 into 12070 into 10 to the power minus 8 upon 4.2 NP NS, right. Now, NP NS will get 27427, right, or because NS we have given that NS is equal to 4 times of NP, it is given already, right. So, I can write that NP square I will get equal to 6856, right. So, NP will be equal to, so NP almost equal to 83, right. We take NP, now we take NP equal to 85 say, and NS we have taken equal to 4 times 340, right. So, if I write down all the design parameters of the LVDT which we have designed, so it will look like this. So, complete design of LVDT, LA equal to 20 centimeter, right, RI equal to 1 centimeter, then RO equal to 4 centimeter, then P primary length 14 centimeter, S is 20 centimeter, number of turns in the primary is 85, number of turns in the secondary is 340, right. So, this is a complete solution to the problem number 12.3, right. Now, let us do one problem on the pH meters. We have solved the problem on the pH meter. We have already done pH sensors in the lesson I think 20. So, we will solve some problem on the pH also. Let us go back. Okay. Problem number 21.4. It problem is telling in order to calculate the pH, the following arrangement is made. A pH electrode is connected through a shielded cable to a non-inverting amplifier as shown in the figure. We will show the figure. The input resistance or impedance of the non-inverting amplifier is given by R equal to Ri 1 plus A naught Rf by R1. Okay, everything will be clear in the circuit. So, let us go back. Let us look at the circuit once again. R1 Rf. Okay. Now, Rf R equal to Ri 1 plus A naught Rf by R1. A naught is the open loop gain and Ri is the input resistance of the op amp. Find the output voltage V naught of the following circuit when 225 millivolt signal is generated at the electrode. Shielded cable looks like this pH electrode, and this looks like this. Okay. So, you see this is buffer amplifiers we have used, supposed to be very high input impedance. So, we have used shielded cable. Now, data given. Okay. Let me see whether we have, yes, find the output voltage V naught of the following circuit when 225 millivolt signal is generated at the electrode, right, very small signal was generated. The data given are resistance of the electrode is 10 to the power 8 ohm, right, resistance leakage of the shielded cable is 2 into 10 to the power 8 ohm, right. A naught open loop gain of the amplifier is 10 to the power 5, Ri is the input impedance is 10 to the power 6 ohm, and Rf is 2 kilo ohm and R1 is 1 kilo ohm. Okay. So, this is our, now let us look at the solution. The solution look like this. Okay. Solution to problem 21.4, right. The op amp given in the problem can be represented like below. You see that we can draw it like this. So, plus minus. So, it has a very high input resistance. This is Ri, right, Ri, and this signal is coming here and this signal is coming here. connected here, this is RF, this is R1 1 kilo ohm, and this is 2 kilo ohm, right. Now obviously I can write, you see that RIF is looking from this terminal, RIF equal to RI 1 plus A naught RF by R1, and so RIF equal to 10 to the power 6 1 plus 10 to the power 5 by 1. So, this will give you almost 2 into, it is 10 to the power 11 ohm, okay, quite high input impedance, right. Now, if I draw the equivalent circuit of our measurement systems, it will look like this. Let me draw the first equivalent circuit of the entire systems. This is the pH voltage which we are getting, okay, source impedance, then listen, there is impedance of the meter, then you have an amplifier has a gain of 3, because if you look at the two value of RF and R3, you will find the gain is of 3. So, this is the output voltage. So, this looks like this, right. So, this RS 10 to the power 8 ohm source impedance, this is our pH voltage, and this is the length RL, actually the cable resistance, right. So, this cable resistance or leakage resistance of the cable is 2 into 10 to the power 8 ohm, okay, cable is to the 8 ohm, and RIF input impedance becomes 2 into 10 to the power 11 ohm, that we have just computed, right. So, the leakage resistance 2 into 10 to the power 8 ohm, I mean input impedance 2 into 10 to the power 11 ohm, please note it is 11 if I take. So, it is 11 ohm. So, this 11 ohm, then the source impedance is 10 to the power 8 ohm, and gain of the amplifier is 3, that is we can find because the closed loop gain is 3. So, the RS is the resistance of the probe or the resistance of the sensor, and RL is the leakage resistance. Now, the closed loop gain, obviously what is the closed loop gain of the circuit, that is I already put it, it looks like this 1 plus RF by R1. So, this will give you 3. Now, analyzing the above circuit we can write, that VO will be equal to K VI RL parallel RIF upon RS plus leakage resistance ARL parallel RIF, right. So, which becomes almost equal to 3 into 225, because this is voltage generated by the pH probe, into RL upon RS plus RL. Please note this is almost equal to, right, like this. Why? Because you see that RIF is equal to 2 into 10 to the power 11 ohm, right, which is much greater than 2 into, that means RL, which is equal to 2 into 10 to the power 8 ohm, right, quite obviously. So, this we can write ultimately, we can write 3 into 225 into 2 into 10 to the power 8 upon 10 to the power 8 plus 2 into 10 to the power 8, right. So, this will give you 3 into 225 into 2 upon, okay, let me take eraser, upon 3. So, it is coming up as, since this is in millivolt 225, so this also will be millivolt, 450 millivolt, This is the answer. Clear? Now, let us solve one problem on the McLeod gauge. In low pressure measurements, we have seen that there is a McLeod gauge has a, it is typically used for measurement of the low pressure. Now, McLeod gauge has nonlinearity. So, if you discard the nonlinearities, we can say as a linear sensor, but nonlinearity introduce some amount of error. So, let us look at that. So, the problem will be on that. Let us look at that, right. This problem on the McLeod gauge, this is 21.5 I think, yes 21.5. The McLeod gauge has a bulb of volume. You must refer to the lectures or to the video lectures of the low pressure measurements or the McLeod gauge, right. The McLeod gauge has a bulb volume of 110 centimeter cube, right. The capillary diameter is 1.2 millimeter. Initially, the reading was found to be 3 centimeter. Later, it was found that the observed reading was wrong, and find the error in the measured pressure if the true reading is 2.5 centimeter. Okay. So, the some error has been introduced. So, let us look at that, right. So, solution to problem 21.5, right. The volume of the bulb is given by, volume of the bulb will be given by 11 into 10 to the power 4 millimeter cube, right. The volume of the capillary for the initial reading is given by VC1. Let us take that volume 2 into 1.2 to the power square upon 4 into 30. So, which is giving you 33.93 millimeter cube. So, the pressure P1 in that case, let me take a new page, the pressure P1 is equal to 33.93 into 30 upon 11 10 to the power 4 minus 33.93, which is coming up as 0.09256 torr, right. So, it is coming up as 1.2332 Pascal. Clear? However, the exact capillary volume is, what is the exact capillary volume? The exact capillary volume is VC2 2 into 1.2 whole square by 4 into 25. So, this will give you 28.27 millimeter cube, right. So, the corresponding pressure will be P2, if I take, that is 28.27 into 25 upon 11.10 to the power 4 minus 28.27 is equal to 0.00642 torr. right. So, it is coming up as 0.857 Pascal. So, this is the true pressure. So, therefore, the error is, so error in the measurement is 857, let me take, it is 857 minus 1.2332 upon 0.857 into 100%, which is giving an error of 43.9%, right. So, this is the answer to the systems, right. So, with this I come to the end of lesson 21, where we have solved all the problems. Welcome to the lesson 22 of industrial instrumentation. Actually, in this lesson and subsequent lesson, you will find that we will discuss some of the basic signal conditioning circuits. As you know, the signal conditioning circuits are very much necessary in various phases of the sensors, because we need whenever the signals are electrical, we need to process. We have to process that type of signals, and we need some signal conditioning circuits. So, in this lesson and the next lesson, we will discuss some of the signal conditioning circuits commonly used in instrumentations. This is lesson 22. Now, this is signal conditioning circuits 1. Contents of these lessons: positive and negative feedback topology we will discuss. We will discuss the active filters, we will single amplifier structure. So, it does not matter if the sensitivity parameters are high, because I have exactly designed the resistance value and capacitance value. So, in that case, even though sensitivities are high, I will get the desired value of the filter parameters omega p, q p, okay, omega z, q z and capital K, right. So, it is very cheap, it is very small, noise is also, because if you increase the number of amplifiers, your noise problem will also will be predominant. So, these are the typical problems in the higher amplifier structures. However, we will see that we will in a subsequent lessons that we will go for 3 amplifier structures, where we can achieve this orthogonal tuning. Also, the sensitivity figures will be less. Okay, with this I come to the end of the lesson 22. Thank you.